I am going to discuss about the new topic, and that topic is what here, matter waves. Actually, matter waves, as it is clear, the wave associated with the material particles. So actually, light shows the dual nature, and some phenomena like interference, diffraction, polarization were successfully explained by taking the wave nature of light. But some phenomena like photoelectric effect and Compton effect were explained successfully by taking the particle nature of light. It means light or radiation shows the dual nature. Dual nature means particle nature as well as the wave nature. So if anybody asks to you, it tell me any two properties on the basis of which can be explained by taking the particle nature of light. So that phenomena is what here, photoelectric effect and Compton effect. And de-Broglie was a scientist who, by taking the principle of the duality, he was given the wave associated with the matter. Matter means all the moving particles under the saturation condition. So, according to de-Broglie hypothesis, all material particles in motion have wave nature also. सभी material particle during motion क्या शो करेंगे, wave nature दिखाएंगे. And the wave associated with moving particles of matter are called either de-Broglie waves or matter waves. Now, de-Broglie wavelength of the matter waves means how can we calculate the wavelength of a moving particle? As you know, already I have told you, the wave associated with the moving particle is called de-Broglie waves or matter waves. So actually, suppose the energy of photon, and already I have told in the previous topic, the energy of photon is given by E is equal to h nu. And suppose if m is the mass of the photon, and since photon is moving with the speed of light, so by Einstein mass energy relation, we can write energy of photon is given by E is equal to mc square, where m is mass of photon, E energy of photon, and c is the speed of light. Here E energy of photon, h Planck constant, and nu is the frequency of light. So from here, R mass of photon m is equal to E upon c square. And also you can write at place of E what here, h nu. So mass of photon we can write here h nu by c square, which already I have derived in the previous chapter also. In the moving mass of photon means, remember this, the rest mass of the photon is 0. It means, but moving mass is not 0. So this one is a moving mass or the kinetic mass of the photon, which is given by m is equal to h nu upon c square. Since the photon travel with the speed of light, so the momentum of the photon p is equal to mass of the photon into velocity, and this one is velocity of photon. And simply you can say this is equal to m means h nu by c square into at place of velocity, since photon travel with the speed of light, so c is cancelled by c, so here you will get here h nu by c. And at place of nu by c, since you know at place of nu also you can write c by lambda, or you know nu is equal to c by lambda. So at place of nu by c, you can write 1 by lambda. This one. So at place of nu by c, you can write 1 by lambda. It means p is equal to h by lambda. Or where p is what? Momentum of the photon. H Planck constant, and lambda is the wavelength. So lambda is equal to h upon p. So the wavelength of the photon is given by h upon p. So in this way we can find out the wavelength of the photon. But de-Broglie used these postulates for giving the wavelength associated with a moving particle. Remember this. This is the wavelength of photon which you have calculated. And de-Broglie used this concept to give the wavelength associated with a moving particle in analogous with the light, which is given by, simply you can say, So de-Broglie postulated that the wavelength associated with a moving particle in analogous with the light is given by lambda is equal to h upon p. This one, which is analogous with what here? Wavelength of this photon. Since photon is what here? Energy packet. It means it is possesses the particle nature. So analogous to this wavelength of light or wavelength of this photon, de-Broglie was given this formula for finding the wavelength associated with a moving particle, where lambda, this one is called de-Broglie wavelength, h Planck constant, and p is what here? Momentum of that moving particle. Suppose if the mass of that particle is m and velocity is v, if the mass of that particle is m and velocity v, then you can say here at place of p you can write mv, then de-Broglie wavelength of that particle is given by lambda is equal to h upon mv. And remember this lambda is equal to h upon mv, where this lambda is called de-Broglie wavelength. So the de-Broglie wavelength of a matter or of a particle of mass m moving with velocity v is given by lambda is equal to h upon mv. So lambda is equal to h upon p or h upon mv. This lambda is called de-Broglie wavelength of the matter. Simply, when you will draw a graph like this one here, this graph lambda p, where h is a Planck constant, so lambda is inversely proportional to p, or lambda is inversely proportional to m, lambda is inversely proportional to v. So simply, when you will plot a graph between momentum and wavelength, or mass and wavelength, or velocity and wavelength here. So from here, in this way you can see, in each case you will get a hyperbolic graph like this one, inversely proportional. So you will get a hyperbolic graph, means hyperbola, and here velocity is kept constant, then lambda is inversely proportional to mass, and when mass is constant, then lambda is inversely proportional to v. This one. So in this way you can also draw or you can also observe the graph between wavelength and either momentum, mass, or the velocity of that particle. And from this relation, a very important conclusion you are getting, and that conclusion is what? First one, if v is equal to 0, if v is equal to 0 means if the material particle is in rest, अगर particle rest में है तो उसकी velocity 0, and when v is equal to 0 then wavelength becomes infinite, and wavelength becomes infinite, this is meaningless. It means a particle shows wave nature only when the particle is in motion. If the particle is in rest, then it does not show the what here any wave nature, because in this case wavelength is what here infinite. And second thing, in the de-Broglie waves or in this matter waves, there is no any certain condition, there is no any condition that moving particle is charged or not. It is independent of the charge, while the light wave is associated with the charged particle only, or motion of the charged particle only. So once again I would like to discuss this one. When v is equal to 0, if the body is in rest, particle is in rest, then lambda is equal to infinite. Lambda is equal to infinite. It means the waves are associated with the moving particles only. And second thing is what here? The de-Broglie wavelength does not depend whether the moving particle is charged or uncharged. It means that matter waves or de-Broglie waves are not in electromagnetic in nature. ये electromagnetic in nature नहीं होती हैं. क्यों? Because electromagnetic waves are produced by the motion of the charged particle. क्योंकि इलेक्ट्रोमैग्नेटिक वेव्स जो होती हैं वो चार्ज पार्टिकल के मोशन के कारण प्रोड्यूस होती हैं, लेकिन यहाँ से जो वेव्स बनेंगी ड्यू टू द मोशन ऑफ दीज पार्टिकल्स वो इलेक्ट्रोमैग्नेटिक नेचर की नहीं होंगी, क्योंकि ये जरूरी नहीं है कि ये चार्ज पार्टिकल या ये पार्टिकल जो मूव कर रही हैं ये चार्ज हो या अनचार्ज हो. नाउ de-Broglie wavelength of electron Means how can we calculate the de-Broglie wavelength of electron or de-Broglie wavelength of any particle whose mass or kinetic energy is given. Suppose let us consider an electron of mass m moving with velocity v, then its de-Broglie wavelength is given by lambda is equal to h upon mv. As you know, already I have discussed this one here. The wavelength associated with a moving particle of mass m moving with velocity v is given by lambda is equal to h upon mv. And suppose if mass m, velocity v, so kinetic energy of that particle k is given by half mv square. So from here r v square is equal to 2k by m, 2k by m. So we can say here v is equal to root 2k by m. And when you will put the value of v here, then de-Broglie wavelength lambda is equal to h upon m, and at place of v write down root 2k by m. And when you will take this m inside, then you can write here m square, then 1 m is cancelled by this m, then you will get here is equal to h upon root 2mk. It means de-Broglie wavelength lambda is equal to h upon root 2mk. And we can say here h upon root 2mk. Remember this is the general formula for finding the de-Broglie wavelength of any particle of mass m मूविंग विथ काइनेटिक एनर्जी की. ये फार्मूला किसी भी पार्टिकल जिसका मास मालूम हो और किस काइनेटिक एनर्जी से मूव कर रहा वो मालूम हो, तो बाय यूजिंग दिस फार्मूला वी कैन फाइंड आउट द de-Broglie wavelength एसोसिएटेड विद दैट मूविंग पार्टिकल. ये नहीं है कि ये केवल इलेक्ट्रॉन के लिए, ये फार्मूला इट इज द जनरल फार्मूला फॉर फाइंडिंग द de-Broglie wavelength ऑफ एनी पार्टिकल मूविंग विथ काइनेटिक एनर्जी की. नाउ वी कंसीडर फॉर इलेक्ट्रॉन. तो सपोज electron is accelerated with the potential V, potential difference V, then the kinetic energy for electron, and now I am writing here for electron. Suppose electron is accelerated with the potential difference V, then its kinetic energy K is given by E into V. And then de-Broglie wavelength lambda is equal to H upon root 2MEV, and by using this formula we can find the de-Broglie wavelength associated with the motion of electron or moving electron. As you know, H Planck constant, m, here we will take mass of electron, and V is what here, with what potential difference that electron is accelerated. So by using this formula we can find the de-Broglie wavelength associated with the electron. And since H is a constant, so when you will put the value of H, mass of electron, charge of electron, and when you will solve it, so after solving you will get lambda is equal to, finally after solving you will get here lambda is equal to 12.27 upon root V in terms of mass. So when you will put the value of Planck constant, mass of electron, charge of electron, and you solve it, V is remain here, and you solve it, then finally you will get lambda is equal to 12.27 upon root V in this term. So in this way, suppose if an electron is accelerated with a potential difference which is given V, suppose if the value of V is given, अगर V दिया हुआ है, तो for calculating the de-Broglie wavelength, directly you can use this formula, lambda is equal to 12.27 upon root V in this term. In same way also you can take the other particles like proton, deuteron. So simply for proton you will take the mass of the proton, charge on the proton. For deuteron you have mass of the deuteron. So by using this concept you can find out the de-Broglie wavelength associated with any moving charged particle by putting the value of charge of that particle as well as the charge on that particle. And for the experimental demonstration of the matter waves or de-Broglie waves, deviation and Germer demonstrate it. So deviation and Germer experiment on the electron diffraction. डेविएशन और जर्मर ने ये दिखाया कि इलेक्ट्रॉन डिफ्रैक्शन शो करता है और इलेक्ट्रॉन के पास मास है, जबकि डिफ्रैक्शन कौन सी फिनोमेना थी? वेव्स की फिनोमेना थी. इसका मतलब इलेक्ट्रॉन इज शोइंग द वेव नेचर आल्सो. तो सिंपली यू कैन से कि डेविएशन एंड जर्मर एक्सपेरिमेंट shows or provide the direct verification of the de-Broglie hypothesis of the matter waves on the moving particle. तो डेविएशन और जर्मर एक्सपेरिमेंट ने दिखाया कि मटेरियल पार्टिकल लाइक इलेक्ट्रॉन भी क्या शो कर रहा था? वेव नेचर मीन्स इट इज डिफ्रैक्शन, इट शोज द डिफ्रैक्शन. तो इलेक्ट्रॉन भी शो करता है, न्यूट्रॉन भी शो करता है, लाइक हियर अदर फंडामेंटल पार्टिकल्स like this neutron also shows the wave nature. So deviation and Germer was given only the what here demonstration or for verification of the de-Broglie hypothesis. So in this video this topic is completed, and please also you go through the example as well as the exercise problems and then solve the problems of this exercise. Thank you.